Hi everyone, welcome to this fifth webinar in our series of revision events for GCSE Physics, Biology and Chemistry students in 2019. This one's going to be for GCSE Chemistry students on the subject of structure, bonding and properties. Once again, I see that we have almost everybody now is logged in. We've completed our sound check, so we can just go ahead and begin the webinar. Now, in keeping with the format of the previous ones, again, I'm going to be going through the topics for this webinar in the order in which they were voted. So let me just, so here we are. So this is today's one, structure, bonding and properties. And this is the list of topics for this webinar. Now again, you all, or most of the students in attendance today voted for the topic of these topics which they considered to be the most challenging one, or perhaps the one that they wanted me to go into first. And so I'm going to be going through these in the order in which they received votes. Now, as always, anything that we don't get time to cover in this webinar, you all have access to the private webinar resources page, where you can continue to ask me questions and receive answers and revision support even after this event concludes, all the way up to the end of your final exams in June of 2019. So if you ever need to find that private resources page, you can just go ahead and have a look at the first page of the exam style questions booklet that you received when you booked your ticket for this event, and click this link here. And all of the resources, the interactive video recording with embedded questions, the revision notes and slides and the whiteboard notes for this webinar will all appear there within about 48 hours of the end of this event. And so please do keep the questions coming, and I've already received a lot of questions through the private messaging function, but please do also post your questions on the live chat on that page as well, because it would be nice to get discussions going around the topics that you feel most challenging. Okay, so let's begin with some basic ideas about structure and bonding. Now, before we go any further, the first thing that you all wanted me to cover was the idea of bonding in general and the distinction between chemical bonding and physical bonding. And so I'm going to quickly begin by giving you guys some very important definitions and foundational concepts. Now, those of you who booked tickets for the previous webinar in this series will have already reviewed some of this content, because it's applicable to the topic on atomic structure and the periodic table. So there's a bit of crossover between those two webinar topics, as there is between those two sections of your specification for GCSE Chemistry, regardless of what exam board you happen to be studying under. So very briefly then, let's quickly do a review of the basic ideas here relating to bonding in general, and specifically relating to the distinction between chemical and physical bonding. So when we talk about bonding in chemistry, the general term bond in chemistry, this refers, generally speaking, to an electrostatic force of attraction. And this is between particles. So whether you're talking about chemical bonding and all of the various kinds of chemical bonding, which we'll go into shortly, or you're talking about physical bonding, which is sometimes referred to as intermolecular bonding or intermolecular forces, the term bond just on its own in general, in all of those cases, refers to an electrostatic force of attraction between particles. Now, the term particle, like the term bond, is very general in chemistry. It can mean a number of things. It can mean, for example, atoms, which, as we saw in the previous GCSE Chemistry webinar, are the smallest particles that make up an element. But it can also mean molecules, which are groups of atoms covalently bonded together. It can mean ions. And so the term particle is very general. These are the more specific terms for the different kinds of particles that you're likely to come across in a GCSE chemistry context. Now, the distinction between chemical and physical bonds, generally speaking, is that chemical bonds tend to be electrostatic forces of attraction between atoms. Physical bonds, or intermolecular forces, are forces of electrostatic attraction between molecules. Now, chemical bonds can also be bonds between ions. So let's distinguish between these then. So we've got chemical bonding and we've got physical bonding. And physical bonding, again, sometimes is called intermolecular bonding. So, the definition that we can work with at GCSE chemistry level for chemical bonding is bonding between atoms or ions. And physical bonding is, or intermolecular bonding as the term might suggest, inter meaning between, molecular to do with molecules. Physical bonding is always between molecules. Now, another distinction is that chemical bonding is much, much stronger, orders of magnitude stronger than physical bonding. So this means that it takes a lot more energy to separate two atoms or two ions that have been joined by a chemical bond than it does to separate two molecules which have been attracted together by some kind of intermolecular bond or physical bond. Now that's going to have some consequences when we start to talk about properties, because as we covered in the previous GCSE Chemistry webinar on the subject of atomic structure and the periodic table, it's the chemical bonding between atoms or ions in a pure substance, like for example the bonding between atoms or in an element or a compound. That is what largely is responsible for determining the chemical properties or the chemical reactivity of that substance. So chemical bonding largely determines the chemical properties of a substance. Now, in contrast, physical bonding, or intermolecular bonding as it's sometimes called, this is largely responsible for determining not the chemical properties or chemical reactivity, but the physical properties. So this determines, in large part, the physical properties of a substance. Now again, briefly to remind you, the term substance in chemistry itself has a very specific and exclusive meaning. In ordinary English, because English is a somewhat equivocal language, one word can mean slightly different things in different contexts. So if you're using just ordinary English language, you might hold up, I don't know, a plastic object like this pen, and you might say that the pen is made up of a very hard substance. You might interchangeably use the term material or matter instead. So you can say that plastic is hard matter or a hard substance. Now in both cases, you would be correct, but if you take a different example of wood, you might say that the surface of a wooden table is made of a very hard material. You might also say that it's made up of a very hard substance, but in that case, if you're just using ordinary language, that's fine, because the two words can be used interchangeably in ordinary English. But in chemistry, as with all sciences, words have very specific and distinct rigorous definitions which are not interchangeable. You can't use the word material or matter interchangeably with the word substance. The word substance in chemistry refers specifically to either an element or a compound. In other words, a specific type of material which has its own unique chemical formula because it's composed of a unique combination of atoms. So, chemical bonding is the bonding between atoms or ions, and it determines the chemical properties of elements and compounds or pure substances. So by chemical properties, again, what we mean here is reactivity in essence. So in other words, what will that element or compound react with? How fast will it react? How energetically will it react? And so on. Whereas physical bonding, the kinds of bonds between molecules, this doesn't determine the chemical reactivity of those molecules. What it does is it determines the physical properties of that substance. Now, by physical properties, we mean things like, for example, melting point, boiling point, solubility in a particular solvent, like water, for example, density, hardness, and you could go on with various other physical properties. But these are the kinds of properties which are measurable and observable by making use of physical processes. Melting is a physical process. Boiling is a physical process. Dissolving is a physical process. And so you can use physical processes to observe or measure the characteristics of the physical characteristics of a material, whereas to measure the chemical reactivity of a substance, you would have to actually do chemical changes using that substance and observe, for example, the speed at which that substance reacts, and so on. So this is the general distinction between chemical and physical bonding, and these are the properties which that bonding, which those types of bonding determine. So we're going to be looking at chemical bonding. And we're also going to be looking at the kinds of bonds that exist between molecules. So now, once again, in the last chemistry GCSE Chemistry revision webinar, we went through the definitions of the term atom, molecule, ion, and so on. But just to remind you very briefly, an atom is the smallest particle of an element which still retains the chemical properties of that element. The molecule is a group of atoms which have been chemically bonded together. Now, there are different definitions, and the term molecule is quite loosely used even within chemistry, but it is used rigorously in different contexts. But we're going to stick with that definition here, a group of atoms which have been bonded together. Ions are atoms or molecules which have lost or gained electrons and have therefore got a discrete overall positive or negative charge on them. So an atom is electrically neutral because it has an equal number of protons and electrons when it's unbonded and uncombined. But then by losing or gaining electrons, it can either end up with a net positive charge or a net negative charge respectively. Similarly, molecules, like for example ammonia, NH3, they can gain or lose protons or electrons, which can then give those molecules a net positive or negative charge. Ions are atoms or molecules which have started as electrically neutral particles, but have either gained or lost electrons and have therefore ended up with a net positive or negative charge. So these are some foundational definitions before we go any further. And so the reason why this subject is so important is because chemistry fundamentally is the science of trying to understand the observable properties of matter, the observable, measurable characteristics of solids, liquids, gases, and so on. But those are the observable and observable characteristics. But typically in chemistry, you can only really explain those things by referring to the unobservable, or rather the invisible to the naked eye. So nobody has ever actually seen an atom or a molecule or an ion with the naked eye, or not average molecules anyway. But we make use of these tiny entities, these particles, and the way in which they're bonded, and also the way in which they are arranged within that substance to explain the observable properties of solids, liquids, and gases. Now, you all began to do this relatively early on in secondary school, or perhaps even in primary school, when you started to draw particle diagrams of solids, liquids, and gases, and you were explaining the physical properties of those, their hardness, their density, whether they can flow, whether they keep their shape. You were explaining those observable properties in terms of unobservable entities, particles. And so that really this is really the extension of that very early teaching that you received. And we're going to be going into these things in a little bit more depth. So these are very important definitions. And as always, I'll make these whiteboard notes available to the attendees in the on the private resources page within about 48 hours of this webinar. So let's start now. Now that we've covered that, let's get into the next thing that you all voted for me to cover, which is ionic bonding. So what you're seeing here is a crystalline substance, an ionic crystalline substance. You can see that the crystals have these kind of regular geometric shapes with flat planes and in a semi-regular formation here. Now, like all properties of substances, this can be explained by referring to the types of particles that this substance is made up of, the way that they're bonded, and the geometry of that bonding, the way that they're arranged in space relative to each other. So ionic compounds are characterized by regular arrangements, and these are sometimes referred to as giant structures. And ionic compounds are the compounds which are formed by reactions between metal and non-metal atoms, which go on to form ions which attract each other. So to remind you, let's have a look at the periodic table here. So ionic compounds are formed when you take metallic elements, such as the elements highlighted here to the left-hand side of the periodic table, and again, about 80% or so of the naturally occurring elements here, and even the unnatural, artificially created elements, are metals. The remainder are either metalloids or non-metals. So whenever you get bonding between a metal and a non-metal, typically that bonding will be ionic in nature. So now, the physical properties of these are that they're typically crystalline solids. They are solids with a crystalline structure, and they typically have high melting and boiling points. So, for example, cesium chloride has a melting point of about 646 degrees centigrade. So the crystalline shapes of these substances are due to the internal structure and symmetry of the arrangements of the particles that make up these substances. So these particles, the ions in an ionic compound, are arranged in a geometry which is generally referred to as a lattice structure. So the term lattice structure refers to the repeating geometric pattern into which the ions, the positive metal ions and the negative non-metal ions, are arranged within that substance. So the different particles in the lattice do have opposite charges, and again these are referred to as ions. Now, because they are oppositely charged, they exert strong electrostatic attractions between each other, and this attraction is called ionic bonding. So electrostatic attractions refer to forces of attraction between oppositely charged particles or oppositely charged objects. So now another very general point is that the reason why atoms bond with each other in any manner, whether we're talking about chemical bonding, ionic bonding, metallic bonding, all three types of chemical bonding occur because atoms with incomplete outer shell configurations of electrons are considered to be unstable. They are unstable in the sense that they're in a state of high potential energy, and they stabilize themselves by forming bonds, and this happens in such a way that the outer shell arrangements are completed, and this makes them more stable. Now, before we go any further, I need to kind of make another little note here about the terms stability and instability. So we mentioned in the previous GCSE Chemistry webinar on atomic structure in the periodic table that the noble gas elements, the group 0 or group 8 elements to the far right of the periodic table, are chemically unreactive because they have complete outer shells of electrons. This makes them stable, whereas the other elements in the periodic table all have incomplete outer shells of electrons and are less stable and stabilize themselves by reacting with each other in various ways. So what does the word stability and instability actually mean? The kind of more awake students, typically when I use the term stable or unstable in the context of chemical bonding, will immediately ask, okay, well, what does it mean to be stable or unstable? In the ordinary macroscopic world, stability and instability of objects is a fairly intuitive and obvious thing. So if you have a large object which has a triangular shape balanced on its tip, then it's fairly intuitive and obvious, even to a person who's not a physicist or an engineer, that that situation is unstable. It can topple over with the tiniest little push. Whereas if you take that same object and flip it upside down and sit it on its base, then that object is more stable because it's harder to push over. But what does the term stability and instability actually mean in the context of ionic bonding, covalent bonding, metallic bonding, chemical bonding in general? It's slightly more difficult to wrap your head around. Well, I'm not going to go into the full answer to that question because that would be going into A-level or degree level chemistry territory. But I will say this: you can think about stability and instability of atoms versus molecules in a slightly simplified way by considering them to have either considering a system to either have high potential energy or low potential energy. So when you have two unbonded atoms, so let's just say we have an atom over here and an atom over here. So these are unbonded atoms. With incomplete outer shell arrangements of electrons. So let's just draw one electron. Let's just say this is a hydrogen atom and this is another hydrogen atom. Nice simple atom with a single shell and a single electron in that shell. Now in this state, if we have an axis on the left-hand side here to show potential energy, they are in a state of high potential energy. They are unstable. So this system that we're considering is in a state of instability and as such has a high level of potential energy. Now when these two atoms bond with each other, because they are non-metals, they will bond with covalent bonding, so they will effectively overlap their outer or only atomic orbital or shell to form a bond. So now we have a hydrogen molecule. So this is a molecule in which both atoms have complete outer shell arrangements. Now, because I'm using the example of a hydrogen atom, the outer shell is the first shell. So this brings the system that we're considering, these two atoms, to a lower level of potential energy, and this is characterized as being stable. Now, because energy is conserved, if we've gone from this situation before the bonding takes place to this situation after the bonding takes place, then we've gone from a system which has a high level of potential energy to a system which has a low potential a low level of potential energy, but the energy has to have gone somewhere. Now typically what happens is this energy is given off into the surroundings as heat energy. This change in energy, delta E, from here to here, delta E, the energy change for the reaction, this in this case is given off into the surroundings as heat. So when we go from this situation of this atom plus this atom to this situation of the bonded two atoms, the energy change from this system to this system is given off into the surroundings as heat energy. So this would be an exothermic process. So the production of a bond between two atoms is always exothermic. It's a process by which energy is released by that system into the surroundings because the system has given up its excess potential energy. So this is essentially what we mean by instability versus stability. In general, whether you're talking about the microscopic scale or the macroscopic scale, systems in the universe tend to spontaneously move towards the lowest potential energy condition that they can achieve. This is just one of those very fundamental ways in which the universe seems to work, whether you're talking about things as small as atoms or you're talking about things like boulders sitting on the tops of hills. Generally, those systems, sooner or later, will end up in a more stable condition where there's less potential energy stored in them. Either the atoms will end up bonding with each other to achieve a more stable condition, and the energy is given off into the surroundings, or the boulder will tip over and roll down the hill, and in so doing it will transfer the potential, the gravitational potential that it had, into kinetic energy, and eventually all of that is dissipated into thermal energy into the surroundings. So this is what we mean by stability versus instability. Now conversely, bond making, the production of bonds, or rather the bond breaking, the breaking of bonds, once you've formed a bond between two particles, in order to get them back to this condition, so if that's an exothermic process, then to go back to this condition from here to here, oh, that's a very wonky line, not very good at drawing with graphics tablets. So bond breaking is an endothermic process because you are trying to get the system from a more stable condition to a more unstable condition, and therefore you must put energy in to go from here to here. And so bond breaking is always exothermic, whereas bond making, or rather bond breaking is endothermic and bond making is exothermic. So we're going to be going into this in more depth on the in the webinar that's coming up relatively soon for GCSE Chemistry students on the subject of energetics in chemistry. But there is a lot of overlap between different topics in chemistry, and this applies here. So this is what we mean by stable versus unstable. Now the example that I've just used here is for covalent bonding, but it could just as easily be used to describe if you had a sodium atom here and a chlorine atom here, and they form a bond by transferring electrons to form a sodium chloride formula unit here. So whether you're talking about covalent bonding, ionic bonding, metallic bonding, all forms of chemical bonding they happen because the unbonded atoms with incomplete outer shells are unstable, and they achieve a lower potential energy, more stable condition by completing their outer shells of electrons by engaging in either covalent bonding, ionic bonding, or metallic bonding. So let's move on now. So let's have a look at the way in which the ions are actually formed. So during ionic bonding, the ions are formed when one atom pulls the electron or one or more electrons completely away from the outer shell of another atom, and this causes both of the participating atoms to end up with a complete outer shell configuration of electrons. And again, this gives a much more stable structure. So going back to the example that I just mentioned, if we imagine that here we have a sodium atom, 11 electrons, the atomic number of sodium. Here we have a chlorine atom, 17 electrons, again, the atomic number of chlorine. The outer shell of the sodium atom has 1 electron in it. The outer shell of a chlorine atom has 7 electrons in it. And the maximum number that can be occupied in the third shell, which is the outermost shell of both of these atoms, is 8 electrons. So the easiest way for this system to achieve more stability is for the sodium to give up its outer electron into the outermost shell of the chlorine atom. However, atoms, once again, are electrically neutral. They start off with as many protons as they have electrons. So the sodium, with the atomic number 11, started with 11 protons in the nucleus and 11 electrons orbiting the nucleus, but now it only has 10 electrons orbiting the nucleus versus 11 protons still in the nucleus. Now, if each proton has 1 atomic unit of charge, we have 11 positive charges. But each electron only has one negative atomic unit of charge. So now we have only 10 negative units of charge versus 11 positive units of charge. And so you have 1 more positive charge than you have negative charges. And so the overall charge on this particle is now 1 positive unit of charge overall, because the positives outweigh the negatives by 1 unit. Conversely, now that we've transferred this single electron into the outermost shell of the chlorine atom started off with 17 positive charges in the nucleus and 17 negative charges orbiting the nucleus. But now you've added an extra negative charge. So now the negative charges outweigh the positive charges by 1, and so the chlorine atom has become a chloride ion, which has 1 overall negative unit of charge. So, in general, the group 1 elements will readily lose their outermost electron to complete their outer shell configuration, giving them the same configuration as the noble gas in the same row. So the noble gases are stable. And so another way of saying that atoms achieve stability by completing their outer shell arrangement is to say that atoms achieve stability by getting an arrangement, an outer shell arrangement of electrons, which is the same as a noble gas. Now, because all of the elements in group 1 of the periodic table have atoms that have 1 electron in their outermost shell, like we saw with sodium, they can simply lose that electron in order to gain a full outer shell configuration. And so they will all form unipositive ions, ions with 1 overall positive charge. Now, in contrast, the halogens, the elements in group 7, like chlorine that we saw in that animation, they all have 7 electrons in the outermost shell of electrons in their atoms. And so again, it's easier for them to simply gain 1 electron to complete that outer shell than it is for them to gain a full outer shell configuration by any other means. And so these elements, the atoms of these elements, will readily gain 1 electron from other atoms to complete their outer shell, and again this gives them the same arrangement as a group 0 element, a noble gas element. So because they start off as atoms and they gain 1 negative charge, atoms are neutral until they gain or lose electrons, and so in this case all of the elements in group 7 will form uni-negative ions, in other words, ions that have a single overall negative unit of charge. So, now using this notation, we can say that the sodium atom starts off with an electron configuration of 2, 8, 1, 2 electrons in the innermost shell, 8 electrons in the second shell, and 1 electron in the outermost shell. The chlorine atom starts with a configuration of 2, 8, 7, 2 in the first shell, 8 in the second shell, and 7 in the outermost shell. And so the sodium atom will lose 1 electron to the chlorine atom for this reason. And then when this happens, the ions that are formed have the configurations 2, 8 for the sodium and 2, 8, 8 for the chloride ion. So this is kind of this is exactly what happens in pretty much all of the other ionic compounds, certainly the ones that you're going to come across in GCSE Chemistry. The only difference being that the electron configurations of the ions formed by other elements might be different, but it's the same process. The metal atom loses an electron or 1 or more electrons to the non-metal atom, and in so doing both atoms become ions. The metal atom becomes a positively charged metal ion, the non-metal atom becomes a negatively charged non-metal ion, and the 2 ions, because they have opposite charges, they will pull towards each other because the positive ion is attracted electrostatically to the negative ion, and that electrostatic force of attraction is referred to as an ionic bond. So sodium transfers an electron to the chlorine atom, and in so doing you form 2 oppositely charged ions which are attracted to each other. Once again, that electrostatic force of attraction is the ionic bond. So here we can elaborate a little bit on what we've already said about chemical bonding. Chemical bonding, there are 3 main types of chemical bonding. So chemical bonding, we can say, exists in 3 types. We've just taken a look at ionic bonding, and ionic bonding occurs when a metal reacts with a non-metal. Covalent bonding is when a non-metal reacts and bonds with another non-metal atom. Metallic bonding, which is another form of chemical bonding, is when atoms of metals bond with oh, hang on, let me rub that out. I meant to say metallic bonding. So metallic bonding is when metal atoms bond with other metal atoms. So we're going to look at covalent bonding next. So we can represent the two ions that we've just formed using electron configurations, these so-called dot and cross diagrams like this. Now, in all of the previous diagrams, you've seen the charge on the next to the symbol for the atom in the dot and cross diagram, but it's a bit more correct to show the charge outside of these square brackets surrounding the dot and cross diagram for that ion. Now, the reason for this is because this is the overall charge on the whole ion. Overall, the ion, remember, still contains a nucleus. The nucleus, in the case of sodium, still contains 11 protons. And now the electrons whizzing around the nucleus in these concentric energy levels or shells number only 10. So the overall charge, once you take account of the sodium or of the protons, the positively charged protons and the negatively charged electrons, the protons outweigh the electrons by 1, so the whole particle has an overall charge of 1 plus or just plus. So it's more correct, especially in exams, to show the electron configuration diagrams, these dot and cross diagrams of ions with square brackets around them and the charge of the ion outside of the square brackets to the top right here. So if it's just one positive unit of charge, there's no need to write the 1, you just write plus. And if it's a negative unit of charge, like with the chloride ion, you put square brackets around it and just put a minus sign on its own. If there is more than one positive or negative unit of charge, you put the number first, the number of units of charge, and then a plus, or the number of units of charge and then a minus. So, ions are formed when the chlorine atom pulls a single electron completely away from a sodium atom, and this gives both atoms a full outer shell. And this, again, for the ions that are formed, the ions are much more stable as a result of having a complete outer shell configuration. And once those two ions are formed, which are have opposite charges, the electrostatic force of attraction between this positively charged ion and this negatively charged ion, that force of attraction is what we refer to as a ionic bond. So remember, all bonds are electrostatic forces of attraction. In this case, an ionic bond is an electrostatic force of attraction between oppositely charged ions. So if you were to define the word bond, you would say it's an electrostatic force of attraction between particles. Any chemical bond is an electrostatic force of attraction between atoms or ions. If it's an ionic bond, it's the electrostatic force of attraction between oppositely charged ions. So when we react sodium, the metal, with chlorine, the gas, we're not just taking one atom of sodium and reacting it with one atom of chlorine, like we've just done, we've just shown in the previous animations and diagrams. In fact, even with a tiny lump of sodium and even with a tiny amount of chlorine gas, you're dealing with millions, if not billions, of atoms or molecules. And so it's not quite as simple as it was shown in the previous diagram. It's a little bit more like this. So if we imagine we have sodium metal, we have lots and lots of sodium particles on the surface of the sodium metal. Now, chlorine, being a group 7 element, is a diatomic element under standard conditions. The two pairs of chlorine atoms form molecules. And again, remember, the definition of the word molecule is a group of atoms covalently bonded together in this case. So what happens is that the chlorine molecules collide with the surface of the sodium metal, and a chemical change takes place whereby we have a new substance being formed which has a unique chemical formula which is different from the reactants that we started with. In this case, we've got particles of sodium chloride. So this would be the equation, and we would need to balance this equation, and we would do so by putting a 2 in front of the sodium and a 2 in front of the sodium chloride here. So once you've got lots and lots of sodium chloride being formed, the sodium and the chloride ions, they're all still positively and negatively charged. So in solid sodium chloride, which is simply the same substance as table salt, the sodium ions in that table salt, they can't be too close together, otherwise they will repel each other. Sodium ions are all positive, and if you get two sodium ions next to each other, they're going to repel each other. Similarly, the chloride ions are negative, and so if the chloride ions get too close to each other, they will repel each other also, because they have the same charge, negative charge. And so in an ionic substance made up of positive and negatively charged ions, the ions have to be arranged in such a way that the repulsion between similar charges, between the electrostatic repulsion between the positive ions and the electrostatic repulsion between the negative ions, is minimized, and that the attractive force between the oppositely charged ions is maximized. So if we imagine looking at the arrangement of ions in a crystal of table salt of sodium chloride, we might see something like this in 2 dimensions. So you see here that the formula for sodium chloride is NaCl, because for every one sodium ion there is one chloride ion. But even the tiniest grain of salt is going to be made up of millions of these sodium and chloride ions, and so the way they arrange themselves is in this regular geometric pattern, where each sodium ion is surrounded by, well, it's actually surrounded by 6 chloride ions in 3 dimensions, but we're just looking at this in 2 dimensions. And similarly, the chloride ions are all surrounded on all sides by sodium ions. In this manner, we can maximize the attractive force between these and minimize the repulsive force between like charges. So the force of attraction holding together an ionic lattice structure is the total of all of the electrostatic forces of attraction, all of the ionic bonds between the pairs of ions, oppositely charged ions. And because there are so many millions of them in even a very small piece of ionic material, the total amount of electrostatic force holding together all of those particles is actually very, very large. And this is why the melting points of these substances are very high. You need lots and lots of energy to completely overcome all of those very strong electrostatic forces in that solid material. So in 3 dimensions, this is what that same lattice structure would look like. So we see here that we've got the sodium ions and the chloride ions, and each sodium ion is surrounded in 3 dimensions by 6 chloride ions. And similarly, every chloride ion is surrounded in 3 dimensions by 6 sodium ions. So if we add more and more ions to the structure, the lattice structure, the regular geometry, the regular geometrical arrangement of these oppositely charged ions takes shape, and each ion has 6 nearest neighbor ions of opposite charge. So if we imagine this is the corner of a crystal of sodium chloride, that would correspond to one of the corners on one of these crystals. So we see here the cuboidal arrangement, the roughly cuboidal shape of sodium chloride crystals. This happens as a consequence of all of the regular arrangement, the geometry of the arrangement of sodium and chloride ions in the actual lattice structure. Okay, so let's take a look at another ionic substance before we go any further. So magnesium and chlorine will also form an ionic compound, again called magnesium chloride. So again, looking at these 2 elements in the periodic table, we see that magnesium is in group 2 and period 3. Again, going back to the principles that we discussed in the last GCSE Chemistry webinar, that tells us that each magnesium atom, before it bonds with anything, has 3 shells of electrons. The 3rd shell is the outermost shell, and the 3rd shell has 2 electrons in it. Chlorine is in group 3, period 3 as well, so it has 3 shells, but it has 7 electrons in its outermost shell. Now again, this periodic table displays the actual group numbers. At GCSE chemistry level, you probably won't be aware that the transition elements also have groups, and so consequently this is actually group 13, 14, 15, 16, 17, 18, but for you guys it's enough to refer to this one as group 3, group 4, group 6, group 7, and so on. It's group 5 as well. Okay, so let's take a quick look at magnesium chloride. So if magnesium atoms have 2 electrons in their outermost shell, then the easiest way for them to achieve stability is to give up those 2 electrons and be left with only 2 shells of full electrons. So, full of electrons. So, this is how this occurs. Now in this case, if each chlorine atom can only accept one electron, but each magnesium atom gives up 2 electrons, then you need 2 chlorine atoms to accept each of the electrons which are given up from the outer shell of a magnesium atom. And so magnesium atom has 2 spare electrons in its outer shell, and so stability is achieved by the donation of an electron from the magnesium atom to each of the 2 chlorine atoms, and this gives the 3 ions each a noble gas electron configuration. And so the magnesium atom gives up an electron to each one of these chlorine atoms, and in so doing we end up with a magnesium ion which has a configuration of 2, 8. It's going to give up these 2 electrons and end up with a configuration of 2 electrons in its innermost shell and 8 electrons in its outermost shell. However, in doing this, we've gone from a electrically neutral atom, which had an equal number of protons in the nucleus to electrons around the nucleus, to an ion. We now still have 12 electrons in the nucleus, but we now are about to only have 10 electrons orbiting the nucleus because we're going to give up these 2. And so the magnesium atom becomes a dipositive magnesium ion with 2 overall positive units of charge. Now, just as we saw before, each one of these chlorine atoms is going to form a unipositive chloride ion with a configuration of 2, 8, 8. So now we have an electrostatic force of attraction between this positive magnesium ion and the 2 chloride ions on either side. And so we formed magnesium chloride, and this is the reason that the formula for magnesium chloride is MgCl2. It's because you need 2 chlorine atoms to react with each magnesium atom in order to achieve stability for all of the atoms which are participating in that chemical reaction. And so in any piece of magnesium chloride, the number of chloride ions are going to be double the number of magnesium ions, and so the formula for the substance, the compound, is MgCl2. So now, again, that's what's happening when we consider a single formula unit of magnesium chloride. In other words, a single magnesium and 2 chlorine atoms reacting together to form one formula unit of MgCl2. But as we saw before, this happens on the macroscopic scale by the metal, the surface of the magnesium, reacting with molecules of chlorine. In this case, it happens a bit more like this. So once again, it's a chemical change because the product is very different from either of the reactants in its chemical formula. This is just Mg, this is Cl2. And so whenever you have a new substance being formed, which has a different, unique chemical formula to the reactants, then you have a chemical reaction which has taken place. So this time the chemical equation for this process is simply Mg plus Cl2 gives MgCl2. So calcium chloride is very, very similar. Calcium is in the same group as magnesium. It has 2 electrons in its outermost shell, the 4th shell in this case. And so it's going to react similarly to magnesium. As we said in the previous webinar on atomic structure and the periodic table, elements in the same group, because they have the same outer shell configuration of electrons, they will react in a similar way. They will have a similar chemical reactivity. So magnesium is here, calcium is here, and so they both react in a similar manner. The magnesium atom will give up 1 electron to each chlorine atom to form a dipositive calcium ion, and in so doing it will be electrostatically attracted to the 2 chloride ions which are also formed to either side. And once again, the formula of calcium chloride for this reason is CaCl2, because you need 2 chlorine atoms to react with 1 calcium atom in order that all of the ions have noble gas electron configurations. So now we mentioned lattice structures, so I'm going to be talking about metals a little bit later on in this webinar, so I'm going to quickly skip forward a little bit and move on to covalent bonding, which is the next thing that you all voted for me to go through. So we've already talked about ionic bonding. Now, there are 2 types of covalent molecules. Once again, a molecule is a group of atoms which are bonded together by chemical bonds, in this case, covalent bonds. So atoms that bond together to form covalent bonds typically are non-metal and non-metal atoms. Now, this is a bit of a simplification. When you go on to study A-level chemistry and degree-level chemistry, you'll realize that the distinction between this kind of simplification, where covalent bonding only occurs between non-metals and non-metals, ionic bonding only occurs between metals and non-metals. It's a bit of a simplification, but it's okay for GCSE purposes. So we've looked at what happens when a metal bonds with a non-metal to form an ionic bond. The two ions are oppositely charged. They electrostatically attract each other with a strong degree of force, and this then gives rise to the properties of ionic substances. So we'll come back to properties a little bit later on. Now, one thing that I mentioned earlier on, which I forgot to note down, so I'm going to note it down here because it's rather important, is that there is a difference in the strength between chemical and physical bonds. Chemical bonds, whether they're ionic, covalent, or metallic, are much, much stronger than physical bonds in strength. So it takes a lot more energy to break apart two chemically bonded atoms than it does to separate two molecules which have been physically bonded together. But we'll come back to that. Now, in the case of covalently bonded atoms, they are either relatively small, simple molecules, or they can be extremely complex, very large molecules. Now, the basis of life, the reason why living organisms get so complex, is because they're composed of extremely large, complex molecules, things like proteins and nucleic acids like DNA and RNA. The complexity of living organisms is the reason that can exist is that complex molecules with very complex, very large structures like DNA and RNA can exist. Similarly, in industry, we can make use of, we can produce substances called polymers, which are made up of very large molecules. These are called macromolecules, macro meaning large, but covalent molecules can also be relatively small and simple. So things like, for example, hydrogen is pretty much the simplest covalently bonded molecule because it's made of only two of the simplest type of atom, smallest and simplest type of atom. But again, covalent bonds can be used to hold together thousands, tens of thousands, hundreds of thousands of atoms in very large complex molecules, either in biological systems or in artificial substances like plastics, and also in nanomaterials like graphene and graphite and carbon nanotubes and things like that. So let's start by looking at the structure and properties of covalent molecules first, and then we'll go into covalent macromolecules. So simple covalent molecules are exactly what they say they are. They are small molecules bonded together in simple structures by covalent chemical bonds. So things like oxygen, bromine, water, ammonia, methane, sulfur, ethanol, and glucose. These are all simple covalent substances. Now, you can get larger covalent substances, like, for example, DNA. DNA is a covalently bonded molecule composed of millions of atoms. Depending on the organism, it can be many more than that. It can be a smaller number of atoms or a larger number of atoms. But in comparison to these simple molecules, it's fairly clear that DNA and proteins and polymers like plastics and things like that are much larger molecules. So let me skip past this. Okay, so simple covalent molecules such as water have low melting and boiling points. So this is where we get into the distinction between physical properties and chemical properties. The melting and boiling points of water are physical properties of water because they relate to physical changes. When you change water from a liquid to a gas, you're not chemically changing it. You're not turning it into a different material. You are you start with water H2O, you end with water H2O. It's just in a different physical state. And so melting and boiling points are physical properties. Now, physical properties, as I said to you before, usually are determined in large part by physical bonding between molecules. So what we're talking about here is the bonding not within a molecule of water, but between the molecules of water. So when we take a molecule of water, we have oxygen, which is in group 6, so it has 6 electrons in its outer shell, and we have hydrogen, which only has 1 electron in the first shell. And the way that this is bonded covalently, as we'll see, is by means of 2 covalent bonds between the oxygen and each hydrogen. But those are chemical covalent bonds. When you boil or melt water, you're not breaking those because, again, you're starting with water, H2O. Let's say if you're melting water, you're starting with water in the solid state where the water molecules are arranged in a certain manner, and you're ending up with water in the liquid state. But those water molecules are still 2 atoms of hydrogen bonded to a single atom of oxygen. You haven't broken any chemical bonds. What you have done when you melt or boil water is changed the physical bonding between those water molecules. So the melting point of water is 0 degrees centigrade. The boiling point of water is 100 degrees centigrade. Now, in solid water, the water molecules attract each other and are arranged in a particular regular geometry. So if you think back to year 7, 8 and 9, your early education in secondary school, you would have been asked to draw diagrams of the arrangements of particles in solids, liquids and gases. Now at that point you wouldn't have used words like atom or molecule very frequently. You would have simply said particles, and you wouldn't have drawn the particles like this where you're showing the actual structures of those molecules in terms of the atoms and how they're bonded to each other. You would have simply drawn a kind of featureless little circle for each particle. But in fact, molecules do have structure. So I see that we're coming up to the first break after the first hour. So I'll pause here in a second, but just to get you thinking, let's say we take, for example, water. So I'm going to write water here to bring up its structure. So this is the structure of a water molecule. We have a hydrogen atom, an oxygen atom, and we have a bond, a chemical bond, a covalent bond between the oxygen and the hydrogen on this side. We have another covalent chemical bond on this side. So this is H2O. This is the structure of a water molecule, and it is a 3-dimensional object. Now the way that these arrange each other, the way that these are arranged in a liquid are effectively random, and they're about as close to each other as they can get. But in a solid, they are fixed in average positions in a lattice structure, and it's that arrangement which gives solid water its unique properties, in the same way that it's the arrangement of the particles in any solid which will give it its physical properties. So they are arranged in a tetrahedral arrangement like this, where each hydrogen atom is attracted to a region on the oxygen atom of a neighboring water molecule like this by intermolecular bonds, bonds between molecules. When you heat water, when you heat ice to melt it into a liquid water, you're not breaking bonds, chemical bonds between the hydrogens and the oxygens, you're breaking intermolecular bonds, which are much weaker. In order to separate the hydrogens from the oxygens, you would need a much higher temperature, a much higher level of heat energy to break these bonds apart here. Okay, so I will pause here for a little while, say about 5 minutes, to give you a little bit of a breather. After the next 5 minutes, I will give you guys the chance to vote on whether or not you'd like me to continue with either the topic teaching in the order in which you voted for, or whether you'd like me to review some of the exam questions that you received in your exam question pack for this webinar. I see that Yeah, okay, that's fine. So there's quite a few good questions popping up in the question and answer panel. Please do keep those coming. As I mentioned in the 5-minute sound check in the lead up to this webinar, please don't type your questions into the chat box for this webinar. That's really reserved if you want to send me a private message in case the audio or the video stops working or something like that. So quite a few interesting questions have been asked already in the Q&A panel. Please do keep those coming, and also take the time to upvote the questions that have been asked by the students in your particular Zoom room, the questions that you feel you would like answered first in the Q&A section at the end of this webinar, the last 30 minutes. Okay, so I will give you guys a 5-minute break. After that, we will either continue with more topic teaching. We'll continue talking about covalent bonding, covalent molecules, covalent macromolecules, metals, and so on, or we can review the exam questions. It's really up to you guys. But for the moment, take a 5-minute break, and I will see you shortly to continue. Okay, everyone, we're back after the 5-minute break. Let me just take a look at what you've all voted for me to cover in the next hour. So it seems that across the 4 Zoom webinar rooms for the students joining us from schools, and also in the Zoom room for the private students, almost overall, let's see. Yeah, so it seems like the majority of you, about 66% of you, have said for me to continue with the topic teaching. That's fine. Just please be aware that whatever we don't cover today in terms of the exam questions, I will be uploading all of the complete mark schemes for the exam questions to the private webinar resources page in the next 48 hours. And you will also continue to be able to ask me any questions either about the topics that I'm teaching about or the exam questions, either in the live chat on that page or via the private messaging function. And typically I'll respond to your questions within about 24 hours or so. All right, so let's move on with simple covalent molecules. So when substances melt, it's the physical bonds between the molecules of those substances which are broken. It's not the strong covalent bonds within the molecules. So we have here strong covalent bonds between the oxygen and the hydrogen atoms within one water molecule. When you melt solid water to liquid water or boil liquid water to gaseous water, it's not these bonds that break. It's the intermolecular bonds, which are relatively weak compared to the chemical covalent bonds here. So simple covalent substances, such as water, are either weakly conductive of electricity or don't conduct electricity at all. And the reason for this is that there are no mobile charge carriers within those substances. In metals, as we'll see, you typically have delocalized electrons which are free to move through that entire metal, and it's those electrons which are the charge carriers responsible for electric current. And so things like metals and also things like graphite, because they have delocalized electrons, they are able to conduct electric currents very well. In contrast, simple covalent substances such as water don't conduct electricity particularly well because there are no mobile electrons. So if we're talking about solids such as ice, for example, are relatively strong and hard because the particles are moving vibrationally around these fixed average positions in the regular geometric arrangement that we call the lattice structure. And those particles do not have sufficient kinetic energy to overcome those intermolecular bonds. Now, in contrast, liquids, they don't keep their shape the way solids do. Liquids, which you get by melting a solid, the intermolecular forces are weaker than they were in a solid, and the particles have a greater level of kinetic energy with which to overcome those forces. So the particles in a solid are only able to move vibrationally around these fixed average positions, whereas the particles in a liquid can move translationally. They can move past each other in straight lines and bump into each other and change direction, and they're moving effectively randomly. Now, the reason for this is, again, because the intermolecular forces are weaker and the particles have more kinetic energy with which to overcome those forces in a liquid than in a solid at the same temperature. Now, if we can contrast those with a gas, the particles in a gas are moving much more rapidly, and the forces between those molecules in a gas are much weaker again. So in going from a liquid to a gas in boiling, we have supplied energy to the particles of the liquid with which they can overcome and break those forces even further, and they have more kinetic energy with which to move around. So that takes care of simple covalent molecules in terms of their structure, or rather in terms of their properties, but we haven't yet explained covalent bonding. So let's take a look at covalent bonding before we go on to covalent macromolecules here. Let me just scroll past here. Okay, so covalent bonding. Now, covalent bonding, I've kind of alluded to it in this diagram here, but once again, the idea behind covalent bonding, as with any kind of chemical bonding, is that the particles participating in that chemical bonding will end up with full outer shells of electrons. So let's go back to the example of water. So the elements involved in water are oxygen and hydrogen. So again, to remind you, oxygen is in group 6 of the periodic table. It says 16 here, which is the actual group number, but as far as you guys are concerned, it's group number 6. And so oxygen is in group 6 and period 2 of the periodic table, and its position in the periodic table tells us that it has 2 shells of electrons, the second being the outermost, and in that outermost shell there are 6 electrons, its group number. Hydrogen, on the other hand, has 1 shell of electrons in which it only has 1 electron in each atom. So if we were to draw the outer shell of an oxygen atom, now I'm going to draw both shells. So we have, let me switch back to the other color here. All right, so if I was to draw the first shell and then the second shell, it's the second shell which has 6 electrons. So we have 1, 2, 3, 4, 5, 6 electrons. The first shell is filled, so it has 2 electrons in it already, and this is our oxygen atom. Now, the hydrogen atoms each begin with 1 electron in its single shell of electrons, but that is shared with the oxygen atom, and the other hydrogen atom over here will do the same thing. And so now all of the participating atoms have a stable noble gas configuration. Hydrogen now has its only electron shell, which is the first shell, filled. The first shell of any atom can contain a maximum of 2 electrons, so these 2 hydrogen atoms are stable. And the oxygen atom similarly has now 8 electrons in total in the second shell, which is the maximum number of electrons that the second shell can occupy. And so the water molecule now has all of the atoms participating in it with filled outer shell arrangements of electrons. And so covalent chemical bonding is, again, bonding between atoms that happens in order that those atoms can achieve a more stable arrangement of electrons. Now, it's fairly easy to see in the case of ionic bonding why ionic bonding is an electrostatic force of attractions between ions. Well, the ions are oppositely charged. The metal ion becomes positively charged, the non-metal ion becomes negatively charged. It's fairly obvious why those would electrostatically attract each other. Positives are attracted to negatives. But in this case, we have atoms sharing electrons with each other, and yet covalent bonds, they are chemical bonds, and therefore they must be electrostatic forces of attraction between particles, but we don't see any overall charges here between these molecules. So the question is, why does sharing electrons between these 2 atoms or between these 2 atoms, why does this shared pair of electrons end up causing the 2 atoms to be electrostatically attracted to each other? Now, one of the mistakes that I see a lot of students making is that when they're asked to describe what a covalent bond is, they'll say it's a shared pair of electrons between 2 atoms. Well, it is incorrect. Unfortunately, for a lot of exam boards will accept that as a definition of a covalent bond. it's not actually a very good definition of a covalent bond at all. A covalent bond is a chemical bond is a bond, and therefore it must be an electrostatic force of attraction between particles. And so if you're going to define any of these, you must define it, if you're going to be rigorous with your language, as an electrostatic force of attraction between something and something else. So the reason why covalent bonding is an electrostatic force of attraction. So the reason why this covalent bond is an electrostatic force of attraction between this hydrogen atom and this oxygen atom is because in this oxygen nucleus you have protons. So the nucleus is positively charged here. The nucleus is also negatively charged. The nucleus of a hydrogen atom, rather, is also positively charged. So you have two positive nuclei sitting here and here. You also have another positive nucleus sitting here. And so if we just take this covalent bond here, the reason why it is also an example of an electrostatic force of attraction is because this negatively charged region of electrons attracts and is attracted by these two positively charged nuclei on either side of this pair of shared electrons. So a covalent bond between two atoms. So if we imagine we have atom A and atom B. So let's just say we've got the outer shell of atom A over here, we've got the outer shell of atom B over here, and they are sharing a pair of electrons between them, one from atom A and one from atom B. Well, the nuclei of these atoms are positive. The nuclei of any atom is positive. So this nucleus over here is positive. This nucleus over here is also positive, but this region of negatively charged electrons over here, this is a region of negative charge. So this is negative. And so the electrostatic force of attraction, which is the covalent bond, is the force of attraction which pulls these positive nuclei towards this negatively charged region of electrons. So the covalent bond, strictly speaking, is an electrostatic force of attraction between the nuclei of two atoms which are positive and the shared pair of electrons which are negative between them. This is what a covalent bond actually is. A shared pair of electrons is just a shared pair of electrons. It is a molecular orbital, strictly speaking, containing a pair of electrons. But the covalent bond is an electrostatic force of attraction, and it arises because that region of negative charge made up of that pair of electrons is sitting right between the two nuclei of these atoms. And so the further these two nuclei are apart, and the further away they are from this pair of shared electrons between them, the weaker the covalent bond is. The closer they are to each other and the more positive they are, then the stronger that electrostatic force of attraction is, the stronger the covalent bond is. So that's what a covalent bond is. This is how a covalent bond arises, and covalent bonds are responsible for both simple covalent substances and also giant covalent substances, or covalent macromolecules. So let's take a look now at covalent macromolecules. So inorganic macromolecules so if we talk about the actual term macromolecule, a macromolecule is commonly defined as a molecule made up of over 100 atoms or ions. Inorganic macromolecules are the ones which are not made by living things. So the kinds of macromolecules that living things are made up of are proteins, nucleic acids like DNA and RNA, carbohydrates, like starch, for example, or cellulose, which you find in plant cell walls, and lipids, fats and oils. These are large molecules, but these are organic molecules. These are molecules made by living things. Inorganic macromolecules are the type of macromolecules which are not made by living things, and these generally have a three-dimensional repeating geometric arrangement of the particles that make them up, called a lattice structure. So a lattice is defined as the regular 3D arrangement of atoms, ions, or molecules in a crystalline structure, which are the types of structures that you typically find with inorganic substances. So as the particles are arranged regularly, the material will typically be a solid at a room temperature. Now, there are two categories of inorganic macromolecules. These are defined by the types of bonds within the macromolecule, the bonds between the atoms or the ions. So if the macromolecule is made up of ions, it is an ionic macromolecule. If it's made up of covalent bonds between atoms, it's called a covalent macromolecule. So polymers, which I referred to before, these are organic macromolecules because they contain the elements carbon, hydrogen, and oxygen and nitrogen. Now, organic macromolecules are not necessarily made by living things, but they typically, the ones that they're called organic because the kinds of macromolecules found in living things are made up of carbon, hydrogen, oxygen, and nitrogen, but also most polymers made in industry are also made up of those same elements. So diamond and graphite, these are examples of giant molecular structures. These are made up of very, very large molecules consisting of billions of atoms, all covalently bonded together. And so, in a real sense, a diamond is kind of like a giant molecule, a molecule which is visible, and it's a molecule because it satisfies the definition of a molecule. Each one of the carbon atoms in that diamond is chemically bonded to other atoms. A molecule is a particle made up of atoms chemically bonded together. And so if all of the carbon atoms in a diamond are covalently bonded together, then that structure, that object can be described as a giant molecule. So both diamond and graphite, they're made up of carbon, but they have different properties and uses because the structure, the arrangement of the carbon atoms, and also the arrangement of the bonds between those carbon atoms is very, very different. So we call diamond and graphite allotropes of carbon because they're both pure forms of the same element in the same physical state, solids and liquids, with differing physical properties. So let's take a look at graphite first. So in graphite, the carbon atoms are arranged in parallel layers where within each layer the carbon atoms are arranged hexagonally with covalent chemical bonds between them. So each individual layer of a piece of graphite, even a small piece of graphite, contains many billions of carbon atoms arranged in hexagons. So this carbon has 3 covalent bonds with the surrounding carbon atoms, as you see here. Now, because these are covalent bonds, these are strong electrostatic forces of attraction, and so each carbon is held strongly in its respective layer by these covalent chemical bonds. However, between the layers, you have relatively weaker intermolecular forces. So the distance between adjacent carbon atoms within any given layer is about 0.14 of a nanometer, 0.14 billionths of a meter, whereas the distance between the layers is about 0.34 nanometers. So in graphite, we have this arrangement. Now, when the reason why graphite is used as a lubricant in industrial machinery, and also the reason why if you have a graphite pencil, like this one, now many people refer to the material in the middle of a pencil as a pencil lead, but sometimes they mistake the element lead in the periodic table for what you find in the middle of a pencil. In the middle of a pencil, you don't find lead, Pb. Lead is a metal, a kind of dense, greyish, unreactive metal. The part of a pencil called the lead of the pencil is actually made of graphite. Now, the reason why when you move this along the surface of a piece of paper, it leaves behind a line, is because the layers of graphite atoms, these hexagonally arranged layers, can slide over each other. And this makes graphite a soft and slippery material, and this is why it's used as in pencils, obviously, but also in as a dust, which is then sprayed over the surfaces of very large parts of industrial machines that articulate against each other to help to lubricate those different parts so they slide over each other and the metal doesn't become damaged. Now, charcoal is also another rather widely used and well-known form of arrangement of carbon, and it's carbon arranged in microcrystals of graphite where the layers are randomly oriented. So that's the structure and the bonding within graphite. Let's take a look at how that relates to its physical properties. So let's take the melting point, for example. Now, graphite has a very, very high melting point of about 3,730 degrees centigrade. Now, the reason for this is that even though the layers of graphite are able to slide over each other relatively easily, the intermolecular forces between those layers are relatively weak, and that causes them to be able to slide over each other. However, the bonding between the carbon atoms in each layer is strong covalent bonding, and so in order to separate all of those carbon atoms and enable them to move around in the liquid state, you are having to overcome chemical bonding as well as intermolecular bonding. And so graphite has a high melting point for that reason, and similarly, for the same reason, it has a high boiling point as well of 4,830 degrees centigrade. So because it can withstand these kinds of high temperatures, another application, another use of graphite is in foundries, where it's used to make industrial crucibles for heating metals. Now, the covalent bonds between the carbon atoms in these layers of graphite are so strong that when you make graphite fibers with their layers arranged along the fiber, these are stronger than steel, and this makes carbon fiber, which is made of graphite, ideal as a reinforcement for things like tennis rackets and squash rackets. It's also used in medicine as a reinforcement for broken bones, and you're seeing that here in this X-ray. So I mentioned that graphite is electrically conductive, which is rather unusual for a pure non-metallic element. So the reason why it's electrically conductive has to do with the way that these atoms are arranged in these hexagonally arranged layers. So carbon, if we take a look at the periodic table here, so carbon is in group 4 of the periodic table and in period 2 of the periodic table. So if we were to use that information to construct a dot and cross diagram of the arrangement of electrons in a carbon atom, we would arrive at something like this. So we have the symbol, let me go to a different color here. So we have the symbol for the element, we have two shells, so let's draw the first shell. And we have the outermost shell, which is the second shell in the case of carbon. Now, this carbon atom has 4 electrons in its outermost shell. So there's 1, there's 2, there's 3, and there's 4. So the underlying shell, the first shell, has a maximum of 2. It must already be filled. So this is an unbonded carbon atom. Now, what this means is that each carbon atom can form a maximum of 4 covalent chemical bonds. Now, it does this in something like methane, for example. So methane is CH4, and in methane, each carbon atom will share its electron like this, in a similar way to this, will share each one of these 4 electrons with 4 hydrogen atoms, and this will form a molecule of methane. So let me just draw, rather I'll just type in methane here, and it should give you the structure. So this is a molecule of methane. And you can see here that the carbon atoms are tetrahedrally arranged, like this. So this carbon atom now has a full outer shell of 8 electrons because it started with 4, but it's sharing 4 electrons from with each one of these hydrogens. So this is a pair of electrons, this is a pair of electrons, this is a pair of electrons, this is a pair of electrons. So we have 8 electrons in total in that second shell. and this is methane. However, in graphite, the situation is rather different. In graphite, we have a slightly different situation here, where we have only 3 of these electrons are being shared with surrounding carbon atoms. I'm not going to draw the entire carbon atoms here, so this would be one of their outer shells. This would be another one over here, where it's sharing an electron here. There would be another carbon somewhere over here, sharing an electron. But now we see that we have this unshared electron here, sitting in the outermost shell. So in graphite, this unshared electron from each carbon atom is delocalized. Now what I mean by delocalized is it is given up from this carbon atom and is able to move freely between the layers of carbon atoms for this reason. So these delocalized electrons literally will flow between these layers like this, will be able to move between the layers, the hexagonally arranged layers of carbon atoms. And so this this freedom of motion of these delocalized electrons allows materials like graphite to conduct electricity rather well. So graphite is conductive, electrically conductive for that reason. So, as a result, graphite can be used as electrical contacts in various materials, and also in various applications like these, as well as being used in industry in the ways that we've already discussed here. So it's used in for electrodes in electric furnaces. It's used for the brushes next to the split ring commutators in electric motors. It's used as the positive terminal in dry battery cells like these, and so on, because it is electrically conductive. Now in diamond, each carbon atom actually has the same arrangement of bonding that you see here in methane. The only difference is that in diamond, each carbon atom is bonded tetrahedrally like this to 4 surrounding carbons. Each one of those is bonded tetrahedrally in the same geometry to 4 other surrounding carbon atoms. So in diamond, all of the carbon atoms that make up a piece of diamond are arranged in such a way that each one is bonded by 4 very strong covalent chemical bonds with 4 other surrounding carbon atoms. And so this arrangement extends all the way through the whole diamond, and this gives rise to the giant 3-dimensional structure of that diamond. So again, the structure gives rise to the properties. So because you have the hardness of diamonds. Diamond is the hardest substance, and the reason why it has this extreme hardness is firstly because all of the particles, all of the atoms that make up that piece of material are held or are bonded to all of the other particles by extremely strong covalent bonds. And also the tetrahedral arrangement of the atoms makes the structure extremely stable so that it can withstand very large forces in all directions. So this this unique hardness of diamond gives it some very useful applications. So for example, it can be used in saws as diamond blades or diamond drills to cut through very hard materials. It can also be used in tile cutters. It can be used as in the surfaces of glass cutters, and so on. Now powdered diamond can also be used as abrasives for smoothing very hard or rough materials down. So diamond has a lot of uses in industry for this reason. Now, the more obvious use of diamond is in jewellery. So jewellers will cut diamonds at precise angles to produce a faceted structure. Now, the reason why diamond has that unique sparkly property to it is because light slows down dramatically in diamond. And again, this is because of the close packing and the tetrahedral arrangements of the atoms in a diamond, and also the arrangements of the electrons in those bonds. So this gives diamond its characteristic glittery property. The white light enters the diamond and then slows down in that very dense medium. And so the light undergoes significant refraction for this reason, and also total internal reflection at the inside of the faceted surfaces. And this is what gives rise to the sparkly nature of diamonds. The light can also be split into its constituent colours, and so the light that escapes from a diamond is often coloured, and this also accentuates and augments the sparkliness of diamonds under any intensity of light. So each of the diamond's dozens of facets will produce its own dazzling display of colours as it's moved around relative to the position of your eye. So diamond, as you might expect, with all of that enormous amount of force holding it together with all of those strong covalent chemical bonds, has a very, very high melting point of about 3,547 degrees centigrade. And again, this is because the carbons are held together by very, very strong covalent bonds. The atoms are not free to vibrate fast enough to break away from the neighbouring carbon atoms until you reach exceptionally high temperatures. Now, unlike graphite, diamond doesn't conduct electricity particularly well because, again, all of those carbon, all of the electrons in that carbon atom in diamond are shared with surrounding carbons. So if this was a diagram of the bonding in diamond, I would have to draw another carbon atom sharing its electron with this one, so that each carbon has a total of 8 electrons in its outermost shell. And so with no delocalized electrons available, diamond does not conduct electricity the way that graphite does. So one of the slightly more recent innovations with carbon allotropes are the fullerenes. Now these were named after R. Buckminster Fuller, who was a extremely important engineer and scientist. So fullerenes are a family of carbon allotropes. So they were discovered in 1985, where microscopic amounts of carbon-60, in other words, a molecule of carbon made up of 60 carbon atoms, which are arranged in this manner, and other related structures were discovered on a very sensitive laboratory instrument. So this is a diagram of Buckminster fullerene, named after R. Buckminster Fuller. And this was the first fullerene that was discovered. So this resembles a football. Now the reason why it was named after Buckminster Fuller is because Buckminster Fuller, as an architect and engineer, he pioneered the use of geodesic domes for architectural purposes. So he built and designed a lot of buildings which used dome-shaped structures, which had struts, which were kind of arranged in a similar manner to this. So this structure kind of resembles a football, and sometimes this is for this reason it's called a buckyball for short. So this is a molecular model of yet another fullerene. Buckminster fullerene is a black solid. Now it does have some interesting properties. So it is soluble in petrol, and this when it does dissolve in petrol, it gives a deep red solution. Now the caged structure of fullerenes like this one gives them a lot of potential uses for things like drug delivery systems, where they can carry the drug, a drug around the body inside this molecular cage, and then allow it to be developed, allow it to be delivered to a particular part of the body where it's released from that packaging system, if you like. It can also be used to remove pollutants from the environment, as well as things like or harmful chemicals from the body, by trapping those chemicals within the fullerene molecular cages prior to them being removed. So another application of allotropes of carbon is the carbon nanotubes. So further development of the fullerene family resulted in the development of these carbon nanotubes. This is a diagram of one of these carbon nanotubes. So nanotubes are cylindrical structures which have been made by joining fullerenes together. One end of the nanotube can be capped by a hemisphere of a fullerene, like this. So carbon nanotubes are extremely strong, because if you imagine them as a kind of molecular rope, then that rope is held together by extremely strong networks of covalent chemical bonds, like you're seeing here. They can also be extremely good conductors of electricity because, again, you can see here each one of the carbon atoms is bonded to only 3 surrounding carbon atoms, and so you can have a flow of electrons along the carbon nanotube. They can also be good conductors of heat for the same reason. The reason why metals are good conductors of heat is in large part because they have delocalized electrons which can not only transfer electrical energy as an electrical current, but they can also transfer heat energy from one end of the metal to another. And the same thing can be said of carbon nanotubes. So a lot of the potential uses of carbon nanotubes are actually quite exciting. In 2006, they were alloyed into some of the carbon fiber racing bikes used by professional cyclists. Because of their tubular structure and large surface area, carbon nanotubes incorporated with metal ions have been used as industrial catalysts to achieve very, very high efficiencies in industrial chemical processes. Now recently, carbon nanotube membranes have been developed to remove salt from seawater, to desalinate seawater, and this can be done with a relatively low cost and low environmental impact. So there's no CO2 being produced by burning fuels, for example, which were associated with more conventional methods of water desalination. Now, the reason why water desalination is such a important area to develop new technologies is because there's a rapidly developing clean water shortage in many parts of the world. But 3/4 of the Earth's surface is covered by seawater. If you can find a relatively cheap method of removing dissolved salts from seawater without having to resort to distilling it, which obviously requires you to heat it up and vaporize it and then condense it, and this normally would require the burning of fossil fuels. If you can do that more cheaply and more efficiently with things like carbon nanotubes, then obviously this could go a long way to solving some of the problems associated with the shortage of clean water around the world. Okay, so we've talked a lot about covalent bonding, both simple covalent substances, giant covalent substances, and so on. Let's take a look now at metals. So we've talked about 2 types of chemical bonding so far. Bonding between atoms and ions. So we talked about when we have a metal atom bonding to a non-metal, the metal loses an electron to the non-metal to form 2 oppositely charged ions, a positive metal ion and a negative non-metal ion. They attract each other, and this electrostatic force of attraction is a ionic bond. We looked at what happens when we take 2 atoms of non-metals and bond them together. Each atom shares one of its electrons with the other atom. This helps complete the outer shell structures, and in so doing, the positively charged nuclei of the 2 atoms are attracted to the region of negative charge density, which is caused between them by the shared pair of electrons between them. And so that electrostatic force of attraction is what we call the covalent chemical bond. So what happens when metals bond with metals, and what are the properties of metals, and how can we explain those properties in terms of metallic bonding? So let's take a look at metals now. So solid metals, like other crystalline solids, are composed of particles arranged in a regular geometrical pattern called a lattice structure. So we have here a diagram showing the closely packed metal atoms in a metallic lattice structure. So a large gold nugget is being shown here, and you can see here crystals of gold. And so the pure gold is a metallic structure, and as such it is a crystalline structure because the atoms of gold are arranged in this regular geometry, and this gives rise to these regular flat surfaces of the crystals of gold, one of which you're seeing here. Now, the tight packing together of the atoms and also the high atomic mass of those gold atoms contributes to the reason why gold has a very, very high density. Now, the external regularity of these flat-shaped surfaces, this again reflects that regular, orderly, internal geometry that we call the lattice structure. So the layers in a metal, the layers of particles in a metal, are packed one on top of the other in a lattice structure. Now, this gives rise to many of the characteristic properties of metals. And so things like the malleability, the ductility of metals, these are all a consequence of this arrangement of metals in the metallic lattice and a consequence of the type of bonding that sticks these metals together with electrostatic forces. And in this case, that's a type of chemical bonding called metallic bonding. So a more detailed model of a metallic lattice describes that lattice as having an outer layer of mobile electrons that can jump from one atom to the next. This arrangement has been described as metallic meatballs in a fluid electron soup. So our model of the lattice can now be changed from this to something a bit more like this. So a lot of the time you'll hear these analogies being used to describe metallic bonding. Sometimes the delocalized electrons between these metal ions are described as a sea of delocalized electrons within which the metal ions float. So what's actually happening here? So if we imagine, for example, we take a metal from group 1. So let's say we take sodium, for example. So sodium metal looks a bit like this. It's typically stored under oil, but it's a kind of grey metal that cuts very easily. Now, each one of these sodium atoms has an atomic number of 11 and therefore has 11 electrons in the shells surrounding the nucleus. But that would be an uncharged, electrically neutral atom where you have 11 protons, 11 positive charges and 11 electrons. But as we saw, it's in group 1, and so each one of those atoms has 1 electron in its outermost shell. As we saw before, the sodium atom can achieve stability relatively easily by giving up that electron to a non-metal atom like chlorine and forming an ionic bond with it. But what if you just have sodium atoms in a lump of sodium? How do each one of those sodium atoms achieve stability? Well, they achieve stability by sharing those outermost electrons with each other, because the ion which is formed when a sodium atom gives up that outer shell electron, as we saw before, has a stable electron configuration of 2 electrons in the innermost shell and 1 electron in the second shell, 8 electrons in the second shell, which has become its outermost shell. So each one of those sodium atoms, when you have lots of sodium atoms, will give up its outer shell electron. The outer shell electrons will be shared equally between all of these sodium ions, but these have become sodium ions now because a sodium atom starts with 11 protons, 11 positives, and 11 electrons. If each one of these has given up 1 electron, each one of these now has 11 positive charges and only 10 negative charges. So now each sodium atom has formed a sodium ion, a positively charged sodium ion. But all of this is held together by this sea of negatively charged delocalized electrons, and the electrons act as a negatively charged glue which attracts together all of these positive charges, because again, positive charges are attracted to the negative charges flowing between them. So the outer shell electrons are free to roam around these spaces between the positive ions in the lattice, and it's these free electrons which are responsible for example, the thermal conductivity of metals such as copper. So copper can be used as to make things like saucepans, where the high thermal conductivity of copper is an advantage. The thermal conductivity and also the durability of transition elements like copper is perfect for things like cookware and also for other thermal applications like boilers and things like that. So electrical conductivity, as we said before, is also due to the delocalized electrons which are able to move freely through the metal. The hardness of many metals. Now, sodium is a relatively soft metal. Now, the reason why it's a soft metal is because each sodium atom only donates 1 electron into that delocalized sea of electrons, and each sodium ion only has 1 positive charge. But the transition elements can donate multiple electrons into that sea and also end up with multiple positive charges. And so the degree of electrostatic force of attraction holding those ions together in the metallic lattice is much higher. And so the transition metals are hard and strong typically. There are a few exceptions, like for example mercury is a transition element, but mercury is a very strange transition element that has some very odd properties. It is the kind of exception to the rule. Generally speaking, they have They tend to be quite hard, quite strong. They have a high tensile strength, which makes them very useful in a whole range of different applications in building, defense, security industries, and so on, making tools and various other applications as well. Now, ductility. Ductility is the property of metals that allows the metals to be drawn into thin wires, and the wires then retain their shape. So ductility is an important property of metals, which allows them to be drawn into wires, and as you can see here from this suspension bridge, we can then use that property in many different applications here. Now, another characteristic property of metals is their sonorousness. The fact that when you take a sheet of metal and you strike that sheet of metal, it will produce a characteristic ringing sound. So this is referred to as the sonorousness of metals. Now, the sonorousness of certain alloys of metals like brass and steel, this accounts for the sound quality of various musical instruments and also bells. So here's one of the applications of many of the applications of sonorousness in metals. Malleability is another property of metals, which allows them to be hammered into shape, and then they will retain their shape when you bend them and hammer them. And this is how bells were created. So in early times, a planishing hammer together with a stake and anvil were used to produce brass domes and bells like this brass dome on an old train engine. This was actually beaten into shape, which is actually quite amazing when you look at how smooth the surface looks. Now, the shininess of metals is also due to the structure and the bonding within the metal, and, surprise, surprise, this is also due to the delocalized electrons. So the electrons are free to migrate around the atomic lattice, and it's that property which allows the surface of the metal to reflect light to the degree where it looks shiny in this manner. So here we can see different kinds of metals and also the alloys of different metals and their various different kinds of reflectivity. And this is all as a result of, again, the delocalization of electrons around those metallic lattices. Now, the durability of metals is again due to their structure and bonding. So metals like gold, for example, gold is extremely unreactive. Even though it's not very strong or hard, it doesn't corrode, it doesn't form compounds with surrounding oxygen in the air, and if you take a piece of pure gold and you bury it in the garden in swampy, boggy soil, it can stay in that soil for thousands of years, and then if somebody, some archaeologist in the future, thousands of years from now, digs it up and then cleans it off, it's pretty much as shiny as it was when it went under the soil. So gold is valuable not just because of its shininess and its attractiveness, but also because of its durability. So the durability of iron and steel is another example, and this is the reason why steel is used in so many structures for buildings and things like that. So metals in general are durable, and so all of these objects are quite old, some older than others. Now the external parts of some of them have corroded, as you can see here, but some of them have almost not corroded at all, like this one here, which is thousands of years old. So the value, metals are valuable, and the rarity of certain metals will determine just how valuable they are. Now this is something of a simplification and somewhat naive, unfortunately, because the price of gold, for example, is fixed arbitrarily by bankers in London every week, I believe. But nonetheless, the general attribution of value to things like gold and silver, metals like gold and silver, has been a constant in civilization for nearly 6,000 years. And part of the reason for that is the rarity. Almost all of the gold that's ever been dug up by human beings would basically fit into a couple of Olympic-sized swimming pools, which is pretty amazing when you come to think of just how much human beings have kind of sought after gold and mined gold all over the world. Silver is a lot greater supply, but gold is very rare, and some other precious metals are even rarer still. So the transition metal block is the so-called D block that you find in the middle of the periodic table. And so all of the properties of these transition metals largely are to do with the metallic bonding within them. Right, so it looks like we've come up to the end of the second hour here. So shortly, I'm going to take another 5-minute break. Now, again, during that break, or at least at the end of that break, you will, those of you in attendance should see a poll pop up on your screen where you can vote for whether or not you'd like me to go straight into the Q&A section. There's a few good questions that have been upvoted here in all of the Q&A panels for all 5 Zoom rooms. So please do keep those coming. Or you can vote as to whether you'd like me to continue this webinar for an extra 30 minutes before going on to the Q&A section, and if so, whether you'd like me to continue with the topic teaching, or whether you'd like me to do an extra 30 minutes of exam questions before going into the Q&A. But either way, I'm going to take a 5-minute break, so I suggest you do the same, and when you come back, please do vote for what you'd like me to do, and we'll continue then. See you in a second. Okay everyone, we're back after the second 5-minute break, so let me just quickly take a look at the poll numbers and see what you guys have voted for to do next. Okay, so it seems like the unanimous consensus is for me to go straight into the Q&A. That's fine. Again, I will make the complete PowerPoint for this webinar available to all of you on the or the slides, the images of the slides of this PowerPoint, I should say, available to all of you on the private webinar resources page. So you will get all of that. And again, if you have any questions between now and the end of your exam period in late June on any of these topics, even the ones that we haven't gone over, please do either send me a private message via that page or type the questions that you have into the live chat on that page, and I'll happily respond to any questions there. Okay, so there's a few very good questions that have been asked in the Q&A box for each one of the 5 Zoom webinar rooms. So let me just quickly scan across those and see which ones have got the most votes from all of you, and we'll answer those in the order in which they've received votes. All right, so it seems like, let's see here. Okay, so the question that has received the largest number of votes is how do we explain the different strengths of intermolecular bonds between molecules of different sizes? Good question. Okay, so let's quickly run through that explanation. Now, intermolecular bonds, as I said before, are bonds between molecules bonds between molecules. So the simple explanation here, now most GCSE specifications will not require you to explain this in any great depth. They simply require you to understand that the larger the molecules get, the bigger the intermolecular forces between them. So let's imagine we've got 3 sets of molecules, a pair of molecules which are relatively small, a pair of molecules which are a bit larger, and a pair of molecules which are larger still. Let me actually draw that one slightly differently because they're not right. So now the reason why is if these molecules are all neutral, electrically neutral, then there's no real obvious reason why they would be electrostatically attracted to each other. In fact, they are, and the reason for this is that even though they are electrically neutral overall, these molecules, and there's no overall positive charge or negative charge here that would cause them to attract each other, the surfaces of these molecules are the outermost shells of the atoms which are bonded together in these molecules, and the electrons on those surfaces are in a constant state of random motion. So let's imagine that we take a snapshot of these molecules at any given point in time. Now, there is some likelihood that because of the random motion, let's take this pair of molecules as an example. If we take a snapshot of these 2 molecules when they happen to be close to each other, because of random motion, there might be more electrons over this side of the molecule at that instant than there are over this side. Now that would make this side slightly negative, delta minus, delta meaning slightly, than this side. And because the electrons are over this side becomes slightly positive with respect to that side. Similarly, at this instant, because this side is negative, the field, the electrostatic field around this molecule, causes the electrons over this side of on this side of this molecule to be repelled by this slightly negative charge. So the electrons on this side are pushed away by the negatively charged end of the molecule here and end up on this side. So this would be an induced situation. So this is an instantaneous dipole, a dipole separation of charge that exists for an instant due to random motion. This induces or causes the opposite dipole to appear on this molecule, where this side is electron deficient and this side is electron rich. Now you have a negatively charged region of this molecule and a positively charged region of this molecule. They attract each other, and so this is an intermolecular bond. This is actually called a van der Waals force or London dispersion force. Now you don't need to know these terms, but this is how intermolecular bonds arise between neutral molecules. Now, if we look at a larger pair of molecules, it stands to reason that this larger pair of molecules will have more electrons in them. So if we look at the same situation, if you have an instantaneous dipole where the electrons in this molecule, just by random motion, there are more of them over this side than there are at this side, then this dipole has a greater separation of charge. This negative region of this molecule is more negative than this one because there are more electrons in it. Similarly, the induced dipole, when the electrons in this molecule are repelled to the opposite end by this negative region of this dipole, this similarly will be a greater separation of charge. And so because you have a greater dipole, a bigger dipole here and here versus here and here, this electrostatic force of attraction is stronger. Now, if we take an even larger molecule, the effect is amplified even more. So you have more electrons. So by random motion, you get a bigger dipole on this molecule, which induces a bigger dipole on this molecule. So again, we have a situation where this force of attraction between these two molecules is stronger still. Now, another thing that can affect the strength of intermolecular bonding between molecules is not just their size, but their shape. So let's say you have a pair of molecules here and another pair of molecules of a similar size in terms of the number of atoms in them, but a different shape. Let's say this pair of molecules here has the same number of atoms inside them per molecule as this pair, but they're shaped in a kind of elongated shape. So these two molecules are kind of linear molecules as opposed to spherical ones. Now what this means is that when they get close to each other, just by random motion, let's just say this end of this molecule ends up more negative with more electrons in it than this end of this molecule. So this end of the molecule would be delta minus, this end would be delta plus. This is our instantaneous dipole. This induces the opposite dipole on the neighboring molecule. So the electrons in the neighboring molecule are pushed away by this molecule to the opposite end. So this side becomes delta minus, this side becomes delta plus. But because these molecules are linear, these can attract each other more effectively because more of the molecule can get close to the other molecule and vice versa than these ones, which are more spherical. So typically linear molecules will have a stronger amount of intermolecular force between them than spherical molecules, and larger molecules, whether they're linear or spherical, would have a stronger intermolecular force between them. So I hope that answers your question. So the next highest voted question, let's have a look here. Okay, so the question that received the next highest number of votes is, why do the group 1 metals become softer as you go down the group? So good question again. Now this relates to metallic bonding. So there are trends in the physical properties of materials which arise as a result of the types of bonding which exist within those materials. Now in a metal, the type of bonding that exists is a metallic bonding, which is a type of chemical bonding, but it's a similar principle. So let's imagine we have a metal, like a group 1 metal. Now in a group 1 metal, each one of the metallic ions, as we saw in the animation, just has a single positive charge because it's only given up one electron, its outermost electron. And so you have single positive charges, so this is a group 1 metal. If we compare this to a group 2 metal, the ions will have a double positive charge. However, if you go down either of these groups, so this is a group 2 metal, if you go down each of these groups, the ions still have the same charge on them, but the ions get bigger. So if you go down the group, so moving down the group, you still have singly or unipositive metal ions, but they are larger. And similarly, as you go down group 2, you get larger dipositive ions because you get more electron shells. Now, what does this mean in terms of the strength of bonding? So if this is a piece of a group 1 metal, obviously I'm simplifying things here because in fact even the smallest piece of a very small piece of a group 1 metal or group 2 metal will have many trillions of these. But we're simplifying. So between these ions, what we have is negatively charged electrons moving around in a sea of electrons. And it's these negatively charged electrons that act as the glue holding these positive charges to each other. Similarly, it's the same thing in all of these metals. So, now, the reason why the metals get softer as you go down the group is because the positive charge is, the overall positive charge is distributed over a larger surface area or a larger volume here, and so the electric field produced by this object is less intense than the electric field produced by this object, which in turn causes a lower degree of electrostatic force of attraction, a weaker electrostatic force of attraction between these ions and the negative charges between them versus these ions. It's not just about charge, it's about charge density. So it's the amount of charge per unit volume of the ion. If the ions are greater in volume, that 1 unit of positive charge is distributed over a larger volume on the ion, and that in turn gives rise to a weaker electrostatic force of attraction between the positive and the negative here versus the positive and the negative here. Now, if you go from a group 1 metal to a group 2 metal, if we assume, just for the sake of argument, that the ions are of equal size, the charge density is higher in a group 2 metal because the charge is higher and the volume is the same. So it's a higher charge distributed over the same volume, which will also cause a greater degree of electrostatic force of attraction between the dipositive ion and the surrounding electrons, and then between the unipositive ion and the surrounding electrons. So moving down a group 1 metal, the ions get bigger, the positive ions get bigger, and so the amount of electrostatic force of attraction between the ions in the metal gets and the negatively charged sea of electrons, the amount of force between those decreases as you go down the group, because the positive ions get larger and the charge density decreases. As you go from left to right across, between group 1 and group 2, and then on to group 3, the ions get a higher and higher positive charge, and therefore the charge density increases. Therefore, the electrostatic force of attraction between the ions and the negatively charged delocalized electrons increases, and so again they get harder. For the same reason, as you go down group 1, generally speaking, the melting points and the boiling points get less, because again the amount of energy required to overcome these forces is less than the amount of energy required to overcome these forces. Similarly, as you go from left to right, the melting and the boiling point across the group, going from, let's say, lithium, or going from a group 1 metal to a group 2 metal to a group 3 metal, like, for example, aluminium, the melting points and boiling points increase because the charge density of the positive ions is increasing and the electrostatic force of attraction holding together those metals is increasing. So I hope that answers that question. Okay, so let's take a look now at the next highest voted question here. Okay, so it seems like the question which received the next highest number of upvotes is, and it's actually been asked across a couple of the different Zoom rooms, is why do different ionic substances have different melting and boiling points? Okay, again, a good question about physical properties. So let's have a look at how we go about explaining that. So let me just open up another document here. Okay, so ionic substances are made up of positive and negative ions of different elements. So for example, if we take, so let's take a look at our periodic table here. So if we take, for example, let's think of a good example here. All right, so let's take, for example, sodium fluoride versus sodium iodide. So sodium is in group 1, fluorine and iodine are both in group 7. So you're going to form an ionic compound because you're forming a compound between a metal, sodium, and a non-metal, fluorine or chlorine or iodine. So let's take a look at the physical properties of these. Let's see if we can look those up. So let's see, sodium fluoride. Let's take melting point. All right, so 993, let me just quickly make a note of that, 993 sodium fluoride. So that's the melting point of sodium fluoride. So let's compare that to sodium chloride. Melting point, 801. So sodium chloride and sodium iodide. (661). So we see a fairly clear trend here. Sodium iodide. So we see a fairly clear trend here going down the group, or rather looking at what happens when you form a compound between sodium and the elements of group 7, going from the top of the group with fluorine on down the group from bromine from fluorine to chlorine to iodine. We could include bromine in here. In fact, let's just go ahead and look at what happens to sodium bromide, or what the melting point of sodium bromide is. 747. So right in between sodium chloride and sodium iodide. 747 for the bromide. So when we go from sodium fluoride, we get 993 degrees centigrade as the melting point. Chloride, it's 807. Sodium bromide, it's 747, and sodium iodide is 661. So how do we explain this? Well, again, this goes back to the idea that it's the bonding between the particles which determines the strength of the bonding between the particles, which determines physical properties like boiling point and melting point. So if we're talking melting point, we're trying to heat a substance, and we're going from the solid state, where the particles are all arranged right next to each other, almost touching, like this, to a disordered random arrangement where they are arranged, not just arranged randomly, but they're not moving vibrationally like they are here. They're not held together by strong forces of attraction, and they're just vibrating around these fixed positions. They're moving randomly and translationally. They're moving past each other like this. So in order to do this, we need to supply energy to these particles, and when we eventually heat them to the melting point, any further energy supplied is used to break the bonds between or weaken the bonds between these particles in the solid state, such that they're able to move past each other and enter the liquid state. So the stronger the bonds are, the higher the amount of energy required to do so, and therefore the higher the temperature at which that will happen. So let's take a look at sodium fluoride first of all. So fluorine is in the second period of the periodic table, and it is in group 7. So if it's in the second period, once again, this tells us that the fluorine atom has only 2 shells of electrons, the second of which has 7 electrons in it. So if we now imagine what's going to happen when sodium bonds with fluorine, well, sodium, as we saw, is an element which has 3 shells. It's in the third shell. First shell has 2 electrons. The second shell has 8 electrons. The third shell has 1 electron. Oh, 1 electron. So 1 electron in the third shell. And this is a sodium atom. It has the configuration 2, 8, 1 for a total of 11 electrons, 11 being the atomic number of sodium. Now, with fluorine, we have a group 7 element, which is in the second shell. So there's only 2 shells. First shell, in fact, let me draw these electrons as dots. So the first shell has 2 electrons, and the outer shell, which is the second shell, has 7 electrons in it. So 1, 2, 3, 4, 5, 6, 7. Now, so let's think about what happens when the sodium atom forms an ion. Obviously, it's going to give up its electron to the fluorine atom. So if it gives up this got 10 electrons and 11 protons, so now it has 1 overall positive charge. But that electron has been transferred into the second or outer shell of the fluorine atom, so this has now formed a fluoride ion, which has got a negative charge. So this now has the electron configuration 2, 8, so both of these are stable, and these opposite charges on these 2 particles attract each other, and we have an ionic bond. So far, so good. Now, if we imagine what would happen with a chlorine atom now, chlorine is in the third shell. So chlorine has 3 shells, 1, 2, and 3. 3 shells of electrons. The outer shell, because it's in group 7 like fluorine, has 7 electrons. So the underlying shells must already be filled. So this is a chlorine atom. Now, a sodium ion what am I doing here? Right, okay. So sodium ion is just a sodium ion, so we're still going to have a sodium ion with roughly the same size here. I'm just going to draw the outer shell here. So that's the outermost shell of the sodium ion, and it has 1 positive charge, 2, 8. But the chloride ion is larger than the fluoride ion, so this has gained a electron. So this is a chloride ion. It has the same overall charge as the fluoride ion, but because it has that 1 extra shell between the nucleus and the outermost shell, it is a larger ion. This is 2, 8, 8. Contrast that with a bromide ion, then you get an even larger ion because bromine is in the 4th shell. So a bromide ion is going to be this. 3rd, and the outer shell is going to be the 4th shell. So you see that it's going to be a larger ion. I'm not going to draw the underlying electrons because you get the idea, but the outer shell will have 7 electrons in the atom, but once the atom gains the electron from a sodium ion, so again, here's another abbreviated diagram of our, that's a bit too small, make it at least reasonably the same as the one above it for the purposes of this explanation. So here's our sodium ion, and it's become an ion because it's given up its outer shell electron to the bromine atom, so this will have an overall charge of +1+. So this bromide ion, because it's gained the electron from the sodium, it also has the same charge as either of these, but that charge is on a larger ion. So why is it then that, well, if this ionic bond is in sodium fluoride, and sodium fluoride has a melting point of 993 degrees centigrade, why is this melting point higher than the melting point of sodium chloride? Sodium chloride, remember, had the melting point of 801 degrees centigrade. Sodium bromide had the melting point of 747 degrees centigrade. Well, the reason why this ionic bond is weaker than this one, and this ionic bond is weaker still than this one, is again to do with charge density. Now remember what I said about the strength of bonding in metals. In a metal, where did I draw it? Here it is. So in a metal, the greater the charge density, the term density, so mass density, you may have come across in physics, is mass divided by volume of an object. It's the amount of mass per unit of volume. But charge density is another concept which you may not be familiar with, but it is a similar concept. Charge density is when you have a charged object and the charge is distributed over a certain volume of that object. So it's going to be the charge per unit of volume. The higher the charge density, the higher the strength of electrostatic forces. So, because the higher the charge density of a charged object, the more intense the electric field around that charged object becomes, which then causes electrostatic forces to be exerted on other charged objects nearby. So as you increase the charge density in going from a positively charged ion to from a unipositive ion to a dipositive ion, if the volume remains the same but the charge increases, the charge density increases. That means the strength of electrostatic forces between that charged object and other oppositely charged objects will also increase. Well, this is the same principle here. Because you have a positive ion which is the same in all three cases, but you have a negative ion which is getting larger, what we have here is that as we go down from the fluoride ion to the bromide ion, or rather to from the fluoride ion to the chloride ion to the bromide ion, and even further down the group, which we haven't drawn, the iodide ion, the iodide is going to have one extra shell more, so it's going to be even bigger than the bromide ion, but it's still a negatively charged, a uni-negative ion. So as the ions of the group 7 elements get larger, the sodium halide is going to have an electrostatic force of attraction between a positive ion which has the same size and charge density and a negative ion which has the same charge but increasing size. So once again, charge density is what determines the strength of the electrostatic field around these ions, which in turn determines the strength of the ionic bond. If the charge density is equal to the amount of charge divided by the volume, well, the charge is the same. It's 1 unit in all of these cases, but the volume of the charged particle is much larger. So as we're increasing the volume, we're decreasing the charge density, and this leads to a decreased strength of the electrostatic attraction of the negative ion to the positive ion. And this in turn leads to a decreased strength of ionic bonding, which means you need less energy to overcome the ionic bonds in something like this, sodium bromide, or something even like sodium iodide, which has an even larger negative ion, than you need in something like sodium fluoride. And consequently, the melting point decreases as you go down the group correspondingly. I hope that answers your question. Great. Okay, guys, so it looks like we've come towards the end of this webinar. There are some more questions, but it seems like those have actually already been answered in the in the course of the discussion, which has just gone by. So I'm going to stop there. If you have any further questions, please do type those into either the chat on the private webinar resources page, or send me a private message via the private messaging function there. Thank you for attending, and you're all very welcome. Thank you very much for the kind words, and I will see you in the next webinar. Take